In this video, we are going to go over the functioning of an MLP, multi-layer perceptron, or a neural network. It's also called the backpropagation network, has several names, but hopefully with this example that's in Microsoft Excel, it's pretty transparent, try to make it pretty straightforward. Hopefully you'll get a good idea of how each of the values are calculated and how the network trains itself when presented with data. So you downloaded this file from a blog post. At the start of the blog post, there was a link. It said, I think something like prerequisite. So you can read the prior blog post, which kind of goes over the theory of the MLP or the multi-layer perceptron. And so hopefully, if you've gone over that theory, some of this will seem more intuitive and more straightforward. So definitely recommend doing that. So on your screen, you see the file that you just downloaded. I would, you see the security warning. I would enable the content so you can actually run the macro. And this file only has the one tab, so I'll kind of go over the different things that are on here. So we have some network parameters. So if you went over the theory, you'll know that there's a NETA or a learning parameter, it's also called. There's epochs, which is basically how many times do we want the neural network to iterate over the training data. And the default setting is 10. This is our training data. We have 4 examples. So this is x1 and x2. These are our independent variables, and y, the actual output, is our dependent variable. This is our data over here. There are 4 examples, and you might recognize this is the exclusive OR problem, also called the XOR. So, for example, if either x1 or x2 is 1, the output will be 1. If both are 1, the output will be 0. So it's exclusive OR. Okay. So it's a pretty, if you read the blog post, you'll see that this is a problem that's non-linear, meaning you can't really separate. There's no, in other words, in simpler words, there isn't an easy solution. So we want the neural network to kind of train itself to do the XOR problem. I mean, we can do it in our heads. We kind of know that, oh, exclusive OR, if either 1 is 1, only in that case it'll be 1, otherwise it'll be 0. I mean, it's easy for us humans to do it, but for a machine it's kind of tricky. But hopefully, if this works, we'll be able to train the machine as we go along. Okay, so what are the other parameters here? So if you went over the theory, you would have learned that the neurons in the network have an activation function. It can either be something called a sigmoid, or it can be something called a tan hyperbolic. We're using tan hyperbolic here. So it has 2 parameters, has a 2 constant, an A and a B. And we have these sort of heuristically derived values here for A and B that seem to work nicely. And then the architecture of the network. Okay, and that's 2, 1, and I'll explain what that means. So it basically means there's 2 neurons in the first layer, or the hidden layer. This is the hidden layer. So this is the input layer. Okay, so there's like 3 things here that you see. So this is the input layer, this is the hidden layer, and then this is the output layer. This is where the neural network outputs a value. In the input layer, we have our x1 and x2. In the hidden layer, we have 2 neurons, neuron 1 and neuron 2. And then in the output layer, we have our 3rd neuron, neuron 3. And then one of the trickier things, and this becomes really crucial if you're kind of designing a neural network or writing an algorithm, is how do you index the weights of a network? So you'll see these connections that you see here. So these are the weights that are connecting sort of the input layer to the hidden layer, and then the hidden layer to the output layer. Okay, so these are also weights. So this first one, you'll notice it's called, W as in weight, and then 1, 1, 1. Okay, so what does that signify? So the first one here, the first one is that it's connecting neuron 1. Okay, so this one is connecting neuron 1 to what? To output 1. So that's the second one. So it's connecting neuron 1 to, sorry, input 1. Okay, and then the third index is what layer are we talking about? So this is the first layer, and then this is the second layer. Now you can have more than one hidden layer in a neural network, and we'll read about that later when we get to things like deep learning. But you can have more than one layer. So you can have layer 1, 2. So if you have two layers, then we'll have sort of two layers here, and then the output layer will be layer 3. Okay. So that's how this weight is indexed. So the first one is neuron 1. The second one is that input 1 is feeding into neuron 1, and neuron 1 is in layer 1. So if I go to neuron 2, you'll notice that the first one signifies neuron 2, and this weight is connecting input 1 to neuron 2, meaning it's this one. Okay. And then the third one is layer 1. So if I go to the second one, it's saying it's connecting neuron 2 to input 2, meaning it's this guy over here. And that's in layer 3, and so on. The third one, you'll notice is 1B1, and that's a bias weight. Okay, so we're gonna gloss over the bias one for now. It's one of the, it basically scales the activation function up or down, so it kind of shifts it. And it's a useful heuristic in neural networks. Okay, so these are the weights then. Okay, and there should be, I believe, 9 of them. And then the other thing we need in neural network is how do we initialize the weights? How do we start them off? And here we have, so by the way, all these like yellow cells that you see are inputs, so you can change them. So these yellow weights, have some sort of default starting values. I mean, you could change them and kind of see how the neural network behaves differently. And then as the neural network is going along, these weights get copied over here at the very start, okay? And then you'll see them here. So this is when we're going through the forward pass through the network, okay? So we're going forward, and then after it goes through, we'll go backwards once we get the error in the network. So for example, let me set it to 1 iteration and run this. So we've gone forward through the network with our inputs, and then we get an error. So that's here, and then that error propagates backwards through the network. So this is the gradient function. You would have learned that in the blog post on the theory of a network. So the gradient function determines how we adjust the weight. So these are the new weights. Okay, so you can think of this the forward pass. These are the prior weights, and in the backward pass we have the updated weights. Okay? And then that's kind of how we go along, and we iterate till the network learns. So let's try something. Let's set our learning parameters as to say 0.05. Let's have 10 iterations. We'll run it. And this is the mean squared error. And you will notice that it decreases. So this is the sort of the gradient descent algorithm that's embedded in the MLP mathematics that makes, if the learning parameter is small, we'll see this gradual sort of decrease in the error that's presented by the network. Okay. Now let's run it for a while. Actually, I didn't explain y hat. So y hat are the predictions from the network. Okay, so we are trying these predictions to be the same as the actual. So that's how the error will go down. So if you'll notice that the actuals are 0, 1, 1, 0, and the predictions are 0.51, 0.52, 0.52, 0.53. So they're not very accurate. Okay, even if I go to a single decimal point, they're all 1. So that's not the same as y. So we haven't reduced the error enough. Oops. Okay, so we're going to run it for longer and see So let's run it for 100 epochs. So 100 epochs means it's going to go over 100 times through these 4 inputs. And still, so after 100 input output, so you'll see that the mean squared error was going down, 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 and then it kind of plateaued. It kind of stopped. And we're not getting that, we're not getting a reduction in error that's satisfactory. And this is the case with the neural net, is you kind of have to try a bunch of different things. And as we go along, some later blog posts are going to automate this process. I think one of the really exciting things with something called AIXQL will be this automation of the process to kind of go through. The automation will search through a bunch of initial conditions to find an optimal one. But anyway, for now, we're going to do it manually. We're going to change the neta to a big value, say 2. Okay, and I'm going to run it again and see what that does. So with 2, we are basically giving a shock to the system, a little bit of the neural net, and making it learn at a faster rate. And you'll see that the error profile has changed. It's kind of, looks different. And you'll see here that it looks a little bit better. So for example, the first row, it's closer to 1. The next two are closer to 1. The first one is closer to 0, which is the right answer. Okay, this is the right answer, and that's 0.10, so that's kind of close. 0.6, I mean, it's not as closer to 1, but still it's close. And then 0.5, so that's supposed to be closer to 0, and it looks like it is. So if I go to sort of one significant figure here, yeah, there's still an error, right? So we expect 0, 1, 1, 0. We don't have that yet. Okay, so what to do now? Well, there's only one thing to do, and that's to increase the number of epochs. So we're going to go to 500 and see if that changes anything, and the network sort of learns to to discern that pattern, to discern the XOR problem. So it takes a while to run. This is in Microsoft Excel, and you can see all the calculations. They're all like dynamic, trying to make it pretty straightforward for you. So it is slow. And you'll see the error profile has changed. It's kind of going down. It went down fast initially, and then it started plateaued, and then kind of went slower. But look at this. Very interesting. It's doing a much better job. In fact, it is pretty accurate. Yeah, it's pretty accurate. So it's 0, 1, 1, 0, 0, 1, 1, 0. The mean squared error started at 0.9 or 19. It ended at 0.03. And so you can kind of try different things, try different initial weights, different values of the learning parameter. So this is the key one. The learning parameter, is one of the things that changes things. And then you can also, once again, look at the theory blog post that had all the equations, and you'll notice that these equations to update the weights follow that same mathematics that's on that post. And I know it's an annoying bit of algebra, too much algebra for my taste. But hopefully this Excel example makes things clearer, kind of lifts the lid on how an MLP works. And you'll notice in the title that this says MLP Basic. Over the next several blog posts, we're kind of going to enhance this, bit by bit. There are several different things you can do with the neural network to make it perform better, and we're going to explore that. So hopefully slowly we'll build this foundation where, hopefully, if not all, then most of the mysteries of the neural net will be revealed, and then you'll get a very sort of intuitive feel for how the network works. One thing I did explain is this one yellow cell here. And this is basically, you can select the input type. So if this is like input 1, 2, 3, 4, then you can select the first input, and you'll notice that the first input, both are 0. So x1 is 0, x2 is 0. Select the second input, x1 is 1. So x1 is 1, x2 is 0. Okay, so you can kind of select an input and see how the neural network is, it's propagating forwards and backwards through the neural network based on that input. All right. Okay, so that's it. That's the functioning of the MLP in a somewhat basic Excel format. Hope you enjoyed this. Stay tuned for more blog posts coming up where we will explore ideas such as momentum terms in the neural network, memory, retention in the neural network, and some other heuristics that hopefully make the neural network perform even better. Thank you.